Natural gas is one of the most important fuels in the modern world, but it is also one of the least visible. It heats homes, generates electricity, powers factories, and moves through huge pipeline networks beneath cities and across continents. Most of what we call natural gas is methane, a simple hydrocarbon made from one carbon atom and four hydrogen atoms. In its pure form, methane has no color and no smell, which makes it easy to overlook and dangerous if it leaks. That is why gas suppliers add a strong odor, often compared to rotten eggs, so people can detect leaks before they become explosive. Natural gas is often presented as a cleaner fossil fuel because it burns with fewer toxic pollutants and less carbon dioxide than coal or oil. But that simple reputation hides a more complicated story. To understand natural gas, we have to go far back in time. It began as living matter, especially tiny marine organisms that absorbed energy from sunlight through photosynthesis. When these organisms died, some of their remains settled into sediments and were buried under layers of mud, sand, and rock. In oxygen-free conditions, and under rising pressure and heat, that organic material slowly changed over millions of years. The original solar energy became stored as chemical energy inside hydrocarbons such as methane, ethane, propane, and butane. This is why natural gas is called a fossil fuel. It is not created on human timescales, and once a gas field is depleted, it cannot simply be replaced. Every cubic meter burned today represents ancient biological energy released in minutes. Natural gas does not usually exist as one perfectly pure substance underground. It is typically a mixture dominated by methane, often around 95%, with smaller amounts of heavier hydrocarbons and impurities. Depending on the field, it may also contain carbon dioxide, nitrogen, hydrogen sulfide, helium, water vapor, and other compounds. Some gas is found in dedicated gas reservoirs, while some appears alongside oil or coal deposits. In oil production, gas may come up as a byproduct. Historically, producers sometimes vented it directly into the atmosphere or burned it off in a flare because capturing it was inconvenient or uneconomic. Those choices matter because venting releases methane directly, while flaring converts much of it into carbon dioxide, which is still a greenhouse gas but generally less potent in the short term. Before natural gas reaches a stove, power plant, or industrial furnace, it usually has to be processed. Raw gas can contain water, sulfur compounds, carbon dioxide, and heavier hydrocarbons that would damage equipment, reduce fuel quality, or create safety problems. Processing plants remove these materials and separate valuable byproducts. Ethane can become a feedstock for plastics. Propane and butane can be sold as liquefied petroleum gases. Hydrogen sulfide may be converted into elemental sulfur. Sometimes helium, a valuable industrial gas, is recovered as well. This processing step is a reminder that natural gas is not just a fuel that comes neatly out of the ground. It is part of a complex industrial chain that turns a messy geological mixture into standardized products for energy and manufacturing. One reason natural gas became so useful is that it can move efficiently through pipelines. Once gas is cleaned and compressed, it can flow across long distances to cities, industrial zones, and power stations. Pipelines made natural gas a practical everyday fuel because they created a continuous supply system, almost like an energy bloodstream. But pipeline transport also shaped geopolitics. Countries with large reserves could supply neighboring regions, while countries without reserves became dependent on long-term import relationships. Unlike oil, which is relatively easy to ship in tankers, gas was historically harder to trade across oceans because it occupies a large volume in its gaseous state. This gave pipeline geography enormous importance and made gas supply both an economic tool and a strategic. Vulnerability. Liquefied natural gas, or LNG, changed that geography. When natural gas is cooled to extremely low temperatures, it becomes a liquid and shrinks dramatically in volume, making it possible to transport by specialized ships. LNG opened the door to global gas trade, allowing suppliers and buyers to connect even without pipelines. But LNG is not simple. Gas must be cooled in energy-intensive liquefaction plants, loaded onto insulated tankers, kept cold during transport, and then warmed back into gas at regasification terminals. This adds cost, infrastructure, and emissions. LNG gives countries flexibility and can improve energy security, but it also locks in large investments that may operate for decades. That long lifespan is central to debates about whether new gas infrastructure fits a world trying to cut emissions quickly. When natural gas is burned, it often looks cleaner than other fossil fuels. Compared with coal, gas combustion usually produces less carbon dioxide for the same amount of useful energy, far less particulate matter, and fewer pollutants such as sulfur dioxide. This is why many power systems used gas to replace coal, especially where fast-starting gas plants could also balance wind and solar generation. In homes and industries, gas became valued because it provides controllable heat. But cleaner combustion is not the same as clean energy. Burning methane still produces carbon dioxide, and carbon dioxide accumulates in the atmosphere for a long time. So natural gas may reduce some air pollution problems and lower emissions compared with coal, but it does not eliminate the climate problem. The biggest complication is methane leakage. Methane is itself a powerful greenhouse gas. Over shorter time periods, it traps far more heat than carbon dioxide, even though it does not stay in the atmosphere as long. If natural gas leaks during drilling, processing, transport, storage, or distribution, the climate advantage over coal can shrink or even disappear. These leaks can be accidental, from faulty equipment or aging infrastructure, or deliberate, through venting during production and maintenance. Because methane is invisible, detecting and measuring leaks has long been difficult. Satellites, aircraft surveys, drones, and ground sensors are now revealing that some facilities emit much more than expected. This changes the conversation from what happens at the burner to what happens across the entire supply chain. This is why natural gas sits in a controversial position in climate policy. Supporters describe it as a transition fuel, something that can replace coal, support grid reliability, and provide energy while renewable systems expand. Critics argue that new gas projects risk delaying the shift away from fossil fuels and creating stranded assets, expensive infrastructure that may become uneconomic or politically unacceptable before the end of its planned life. Scientific assessments increasingly emphasize that new fossil gas infrastructure only fits climate goals under narrow conditions, such as very strong methane controls and, in some cases, carbon capture. Without those safeguards, building more gas systems can lock in future emissions. The issue is not only whether gas is better than coal, but whether it is compatible with the speed of decarbonization required. Natural gas also matters because it is tied to everyday reliability. Electricity demand rises and falls constantly, and gas-fired power plants can ramp output more quickly than many coal or nuclear plants. That flexibility has made gas attractive in grids with variable renewable energy. But relying too heavily on gas can expose consumers to price shocks. Gas markets can be affected by cold winters, supply disruptions, export demand, war, pipeline failures, and LNG competition. When gas prices rise, electricity prices and heating bills can rise with them. This creates a difficult balance. Gas can support reliability, but dependence on it can also create economic and political risk. Energy security is not just about having fuel available. It is about whether the system remains affordable, resilient, and adaptable. There are also safety and health dimensions. Natural gas is flammable, and leaks in enclosed spaces can lead to explosions. That is why odorization, monitoring, ventilation, and emergency procedures are so important. In homes, gas appliances can contribute to indoor air pollution if they are poorly ventilated or malfunctioning. In production regions, communities may face impacts from drilling, compressor stations, wastewater handling, truck traffic, and local air pollutants. These issues do not always appear in broad national energy statistics, but they shape how people experience the gas industry on the ground. A fuel can look efficient in an energy chart while still carrying local environmental and safety costs. Understanding natural gas means looking beyond the flame to the infrastructure and communities around it. The future of natural gas depends on choices made now. Some existing gas systems may continue operating for years, especially where alternatives are not yet ready or where reliability needs are urgent. But reducing methane leaks, ending routine venting and flaring, improving monitoring, and avoiding unnecessary long-lived infrastructure are key if emissions are to fall. At the same time, electrification, renewable power, energy storage, efficiency, and cleaner industrial processes are changing the role gas plays. Natural gas is not simply good or bad in one sentence. It is an ancient fuel with modern benefits, real convenience, and serious climate risks. The central question is whether societies use it as a shrinking bridge to cleaner systems, or allow it to become another long-term obstacle to leaving fossil fuels behind. If you found this helpful, please like this video and subscribe for more explainers.